Guys, welcome guys. So this is a small topic about these three inequalities. So basically we will prove all of them and describe their relationship. So we start from Young's inequality, Hölder's inequality, and the Cauchy-Schwarz inequality. Okay, by the way, please subscribe to my channel. Okay, so the Young's inequality say that if a is greater than greater or equal to 0, b is greater or equal to 0 are non-negative real numbers, such that if p larger than 1 and q larger than 1 are real numbers, such that 1 over p plus 1 over q is 1, then we have this identity. So it's a to the p divided by p plus b to the q divided by q, which is larger than ab. And the equality holds if only have a to the p equal to b of q. Okay. And the Hölder inequality basically, we are not talking about a major theory. So in this theory, I only talk about numbers. Suppose you have some numbers x1 to xn, y1 to y1, which is real or complex, and you take an absolute value to the power p, and 1 over p, and yk to the q, 1 over q, and then you sum of them, right? So p 1 over p plus 1 over q still be 1, and there will be larger than their product. Okay. And the Cauchy inequality, I think everyone knows, in Euclidean space, right? We just take about two vectors as an inner product. That inner product will less than the norm of the u and the norm of the v. So basically, you can view the inner products. There's a cosine theta term, which I didn't write out, but because the cosine theta term is falls into the -1 or less than 1, so it has this property. Okay. And this is the complex number, but basically it's just the inner product space version, and you can go to see my other videos to prove this. But basically, the complex case is the same as the real case, except for we just change the usual inner products as this one. Okay, I think everyone knows about this. Cauchy-Schwarz. Okay, so the proof is that the proof. So proof I prove Young implies Hölder, and the Hölder implies Cauchy, and finally I prove Young's inequality. Okay, so first one Young implies Hölder, right? So let me just write down. Probably this is the most difficult one, except for proof, right? So we have this a to a p divided by p larger than b to q divided by q larger than ab, right? So to imply Hölder is very easy, right? We just that probably not very easy. Okay, we just that right. Suppose I have this s1 to xn, y1 to yn, which is complex or not, because I will take the absolute value, so it's fine. I can just that a to be the, let's say I let a to be summation, right, xi to the power p. Sorry, I should say summation xi to the power p, and then take a 1 over p, as I call it, maybe ai. Okay, so this is xi. So I can generate this into this, right? I can generate into ai to the pi plus q summation bi to the q larger than the summation ai bi. I can just generate into this because I just take pair, and I let ai to be this, and bi is just the yi divided by yi to the power q, y over q. Maybe I take absolute value here. Okay, and I put in it. I get 1 over p. So this summation ai to the power p, right? This term becomes power p, right? So it becomes this, and the numerator is just this. So to the power p, that p disappear, right? So 1 over q, yi to the q, yi to the q, right? It was larger than ab. So let's say the summation I, so it's xi, yi, right? These two products, and this is the denominator. Somehow I sometimes cannot remember the proof. Okay, so these two can cancel. This is 1, right? So 1 over p, 1 over q, which is 1. So we get the sum of the xi, yi. Okay, so let's Let's change it. So we get the sum of xi, yi. So this is the left hand side. Well, less than xi to the power p, and take a p root, 1 over p roots, and yi and q roots. Okay, and then if you go back to see, this is exactly the Hölder's inequality. Okay, so very good. Now we start from Young's and the proofs Hölder, right? So the next Hölder's proof Cauchy. I think everyone knows about this, right? Because 1 over p plus 1 over q is 1, right? So I can just take p equals to 2 and the q equals to 2. So from Hölder's inequality, I get this one, right? I get this absolute value less than xi to the power this plus the yi to the power this. So basically, this is exactly the Cauchy, Cauchy. Okay, so now, so now we already proved Young implies Hölder. Hölder implies Cauchy, right? So the next is just proof Young, right? Prove Young's inequality. Okay, so proof. There's a many way to prove it, right? But I like this geometry way. So maybe next time, if I have chance, I will go to another video, different ways. So suppose you have f of x function, which f of 0 is 0, right? You should plot it look like this, right? And so suppose this is b, right? This is x and y. This is b. Then what is this area, right? So this area is 0 to b f inverse y dy, right? And this is f of x, right? So at the y direction, this area is just f inverse. And if you just take if you take random a, which a is here, then this area, right? This area is 0 to a f of x dx. Right, so if you see a picture, you get the very easy inequality says that this f of dx 0 to a from 0 to b plus this 0 to b f inverse y. Basically, it's this two part, right? This two area is well larger than AB, right? Because there's a small area which it does not cover. Okay, so I mean if you set B to here and then you say A to here, then the story is exactly the same, right? You still got some area which does not cover. So you will have this inequality. Okay, next I just did the f of x to be, I guess it's xp minus 1. So in this case, f inverse y is just y to the q minus 1. This can be easily checked because once you let f of x to be, if you solve the inverse, right, then you can change the 1 over p plus 1 over q to 1, change into this kind of form. Okay, so we can just put in here, so 0 to a, x to a p dx, plus 0 to y to a q dy b, right? We're larger than ab. So the right hand side is just xp divided by p and a0 plus the y to q divided by q b0 larger than ab. So this is just a to the power p divided by p plus b to the power q divided by q larger than ab. Okay, so this is Young's inequality. Okay, so that's it. So let me just remind you. Oh, by the way, the complex version is basically same as the real version, so you just change it, and you can still use other way to prove it. Okay, so now this video start from the Young's inequality and the Hölder's inequality and Cauchy inequality, and we start from Young to prove Hölder, and the Hölder proof implies Cauchy, and the Cauchy implies, and finally we just prove the Young's inequality. Okay, and you can download this PDF. I will see you guys in the next videos.